Up to this point, we have been considering limits at a particular value of a fixed real number a. For example, we would, let's say, consider a number a. We would have some function f of x, and we would ask the question, well, what happens as x approaches a from the left, and what happens as x approaches a from the right? Then the way to answer that is to go to our graph and examine the behavior of the y values. So then it seems as if the y values are approaching this number right here. Let's call it a. So then symbolically, we would say that the limit as x approaches a of f of x is equal to L. Again, though, the significance of all this is that so far we have only been considering limits at a particular value of a, and a has been a fixed real number. Now, based on the title right here of this section, you notice that we have limits at infinity. What does that really mean? How can we have a limit at infinity? This limit right here, let me circle that, is really a limit at a fixed number a. What does it mean to have a limit at infinity? Well, what it means is the following. A limit at infinity is the limit of a function f of x as x approaches positive infinity, or the limit of a function f of x as x approaches negative infinity. So how is that possible? What is really the significance of all this? A limit at infinity will no longer describe the behavior of f around x equals a. It will now describe the behavior of f as x gets very, very large towards the right and very, very small towards the left. So practically, it's going to be focusing on the question, what happens to the y values as x approaches positive infinity, and what happens to the x values as x approaches negative infinity. This is what limits at infinity are trying to describe. They're trying to describe the behavior of the y values as x grows without bounds on the positive direction and as x grows without bounds on the negative direction. This is why sometimes limits at infinity are referred as the end behavior of the graph. So end behavior of the function f of x, because they're really telling you what happens at the very end of the graph in the positive direction and what happens at the very end of the graph in the opposite end towards negative infinity. End behavior of f of x. So in this particular case, in the case of this function, we can describe the end behavior like this. Number one, we can say that the limit as x approaches positive infinity of f of x will be equal to, let's look at what is happening here. Look at the graph. The graph is growing towards the right without bounds. So the y values are getting larger and larger and larger. So we can say positive infinity. And for number two, the limit as x approaches negative infinity of f of x will be equal. Let's see what happens here. Tracing the graph and moving towards the left, it seems as if the graph will get very, very close to x but it will just approach it asymptotically. So as if the x-axis is a horizontal asymptote. So it is getting the limit pretty much is equal to 0. So then we can now say that the limit at positive infinity of the graph is positive infinity, and the limit at negative infinity of the graph is 0. The point is now is that I'm hoping that you realize that we can now talk about limits at infinity. And a limit at infinity means that you are considering the y values as x approaches positive infinity. And you are considering the behavior of the y values as x approaches negative infinity. So we call these limits right here, these limits right here, limits at infinity. Summarizing some of the things that we just discussed, limits at infinity is another way to analyze the end behavior of a graph. So for example, let's say that we're given this graph right here. This is the same graph that we analyzed in the previous, at the beginning of this video. In this case, we want to focus on what is happening to the behavior of the y values as x approaches positive infinity in this direction and as x approaches negative infinity in that direction. So if you focus on the graph, this is pretty much following the y values here and the y values over here. We said there that on the right side, the limit at positive infinity of f of x is equal to positive infinity. And the limit as x approaches negative infinity of f of x is equal to 0. And what is really nice about the limit at positive infinity is that you end up getting positive infinity. So this limit right here has a special name. It is an infinite limit at infinity. An infinite limit because the actual behavior of the function is infinity. So by having positive infinity over here, if you remember from one of the previous sections, that makes this limit an infinite limit. And because we are considering the behavior as x approaches infinity, you further call this an infinite limit at infinity. I know that it seems a little bit complicated, but just think about it. An infinite limit because the result is positive infinity. And at infinity because you're considering the limit as x approaches positive infinity. This one over here, there's nothing that special about it. The value of the limit is 0, so this becomes a finite limit. So this right here is just a finite limit at negative infinity. All right. So what is so nice about this second limit right here is that we considered a limit at negative infinity and we got a finite result, a finite real number as the value of the limit. This is really making the x-axis a horizontal asymptote. I am going to even go ahead and highlight the x-axis right here because it actually made it quite special by considering the limit at negative infinity and getting a finite real number as the value of the limit, in this case 0. That made the line y equals 0 a horizontal asymptote. And this is fundamental because we can now generalize this result. We can do this, we can say this. We can say that if the limit as x approaches positive or negative infinity of f of x is equal to a number, let's say k, to a real number k, then the line y equals k is a horizontal asymptote. So this is now practically the proper definition of a horizontal asymptote. This is saying that if I consider the limit at positive infinity or negative infinity, and I get a finite real number as the value of that limit, then the line y equals k, and please notice that this k is exactly the value of the limit, then that horizontal line becomes an official horizontal asymptote for the function. Let's analyze the limits at infinity of some of these functions right here. In the first case, right here, as x approaches positive infinity, let's look at the graph. The graph is the blue curve. That graph seems to be approaching the horizontal line, which is at a level of 1. And as x approaches negative infinity, again, the function is getting close and close and close and close to y equals 1 from under the line. So I will write here that the limit as x approaches plus or minus infinity of f of x happens to be equal to 1. So because the limits at infinity and negative infinity is equal to something finite, if you notice 1 is a finite real number, then what does that mean? That implies that the line y equals 1 is a horizontal asymptote. I am going to be abbreviating horizontal asymptote with uppercase HA so that we can become a little bit more efficient here. So y equals 1 is a horizontal asymptote. In this other graph right here on the right, we have something similar happening. As x approaches positive infinity, let's look at the graph. The graph seems to be approaching the horizontal line too. So this level 2 over here. And as x approaches negative infinity, let's look at the graph. The graph is now approaching 1. So we will describe the end behavior as follows. We will say that the limit as x approaches positive infinity of f of x is equal to 2, and the limit as x approaches negative infinity of f of x is equal to 1. What I want you to notice now is that the limits are different on either side. The limit at positive infinity is equal to positive 2, and the limit at negative infinity is equal to positive 1. However, they don't have to be the same for a line to be a horizontal asymptote. As long as I consider a limit at infinity or negative infinity and I get a fixed number as the value of the limit, that is enough to declare that line a horizontal asymptote. So in this case right here, the horizontal asymptote is going to be equal to the line y equals 2. And in this case right here, the horizontal asymptote will be the line y equals 1. In this graph here on the left, the limits at infinity are as follows. The limit as x approaches negative infinity of f of x happens to be equal to negative infinity. If you look at the graph is going down and there's an arrow indicating that it continues going down towards negative infinity. So we do get over here an infinite limit at negative infinity. On the other hand, as x approaches positive infinity, now the limit is approaching L, whatever L is, but L is a real number. So then we say here that the limit as x approaches positive infinity of f of x is equal to a fixed real number L. Well, even though we got an infinite limit at negative infinity, the fact that at positive infinity we have a finite real number as the value of the limit, then this result right here is enough to declare the horizontal asymptote of the function as the line y equals L. So as long as one of the limits at infinity is equal to a real number L, then that is sufficient to declare the line y equals L as a horizontal asymptote. I don't have to have a finite behavior for the limit on the right and on the left. One finite behavior, whether the behavior at positive infinity or the behavior at negative infinity, is enough to consider a horizontal line a horizontal asymptote. In this case, I only had a finite limit at positive infinity. That was enough to say that the line y equals x is a horizontal asymptote. If you look at this graph over here, something very similar is happening. I have a horizontal asymptote, but only because of the behavior of the function at positive infinity. At positive infinity, the graph is approaching L, but at negative infinity, I get an infinite limit as an answer. That is irrelevant though. Even though I get an infinite limit at negative infinity, the fact that at positive infinity, I got a finite real number as the limit of the function, then that makes this horizontal line a horizontal asymptote. So I am going to write here the limit as x approaches negative infinity of f of x is equal to positive infinity. And the limit as x approaches positive infinity of f of x is equal to L. And it is this result right here that makes the line y equals L a horizontal asymptote. So the horizontal asymptote will be the line y equals L right here. Finally, the last graph over here, we notice again that we do have a horizontal asymptote, but that's mainly because of the behavior of the function at positive infinity. As x approaches positive infinity, you notice how the graph keeps oscillating, but it is oscillating and getting closer and closer and closer to L. At negative infinity, the graph actually continues decreasing all the way down to negative infinity. So the horizontal behavior happens as x approaches positive infinity. So I conclude here that the limit as x approaches negative infinity of f of x is equal to negative infinity. And the limit as x approaches positive infinity of f of x is equal to L. And once again, this is the result that makes the horizontal asymptote be the line y equals L. It is exactly because the limit at positive infinity is equal to L, and L is a fixed real number. Just as we had rules for evaluating limits at a fixed number A, we also need rules, we need tools that will help us analyze limits at positive or negative infinity. So the limit laws that we studied in section 2.3, those limit laws also apply to limits at infinity. And that's a great news. So this is what we're going to have. If we know that the limit as x approaches positive or negative infinity of a function f of x is equal to L, and the limit as x approaches positive infinity of a function g of x is equal to m, then the following are true. The following are gonna always be true. So number one, the limit as x approaches positive or negative infinity of f of x plus g of x will be equal to the limit as x approaches positive infinity of f of x plus the limit as x approaches positive or negative infinity of g of x. This is saying that I can go ahead and apply the limit to f, and I can apply the limit to g. And in this case, I am going to get L plus m. So we can follow the same operation as we did with ordinary limits. Then number two, we'll say that the limit as x approaches positive or negative infinity of f of x times g of x, that will be equal to the limit as x approaches positive or negative infinity of f of x times the limit as x approaches positive or negative infinity of g of x. And that's going to equal to L times m. So it is great to know that even with limits at infinity, I can apply the limit to f and the limit to g. We didn't know that we could actually do that. Now we know. Then for division, here we have that the limit as x approaches positive or negative infinity of f of x divided by g of x will be equal to the limit as x approaches positive or negative infinity of f of x, all this divided by the limit as x approaches positive or negative infinity of g of x. So this is going to be equal to L divided by m, as long as m, of course, doesn't equal to 0. Going back to multiplication, the limit as x approaches positive or negative infinity of a numerical coefficient times a function f of x is equal. So this rule is going to tell us that c, because it's a numerical coefficient, can come in front of the limit notation. So that will be equal to c times the limit as x approaches positive or negative infinity of f of x. So this is going to be equal to c times L. And then finally, 5. This is dealing with radicals. This says that the limit as x approaches positive or negative infinity of the nth root of f of x, that will be equal. If you remember back then in 2.3, this is going to say that we can take the limit and we can apply it to the function inside of the radical. So this will be equal to the nth root of the limit as x approaches positive or negative infinity of f of x. And we know that this limit right here, if you go back to the very beginning, is equal to L. So then this will be equal to the nth root of L. Of course, though, here you have to remember that if n is even, In those cases where the index is even, then L has to be greater or equal than 0. As long as all of those conditions are satisfied, this is certainly great news to hear. Even though all of the previous limit laws that were true for ordinary limits at x equals a are also true for limits at infinity, there is one more law, one more property that is only true for limits at infinity. Think of it as a new property. We're going to continue in the count from before. This will be property number 6, but this is only true for limits at infinity. This property says the following, that if you have the limit as x approaches plus or minus infinity of f of x equal to infinity. So you have an infinite limit at infinity, and you have that the limit as x approaches plus or minus infinity of g of x equals to m. That's a finite limit, is equal to m. Then the following is true, and this is the nice realization here, that the limit as x approaches plus or minus infinity of f of x over g of x, that will be equal to, in other words, even though the limit in the numerator is infinity, this property says that we can apply the limit to the numerator into the denominator. So this will be equal to the limit as x approaches plus or minus infinity of f of x divided by the limit as x approaches plus or minus infinity of g of x. If you remember, this was something that we couldn't do with ordinary limits. With ordinary limits, if one of the limits, either the limit of f or g at a, was infinity, we couldn't go ahead and apply the limit to the numerator and denominator. We would say this limit law, this property does not apply. You would have to figure out another way to examine the limit at a. But with limits at infinity, we don't have to do that. This property is telling us that even if this limit in the numerator is infinity, we can actually apply the limit to the numerator and denominator, and the property is going to hold. The property says that this will be equal to infinity divided by m, which is equal to infinity. In the other case, in the reverse case, we can have the limit as x approaches positive or negative infinity of g of x divided by f of x. And again, the property says that even though one of the limits is infinity, we can still apply the limit to the numerator and denominator, and we're going to get an actual result. So this will be equal to the limit as x approaches positive or negative infinity of g of x divided by the limit as x approaches positive or negative infinity of f of x. In the numerator, we're going to have m. In the denominator, we're going to have infinity. And this really means that since the numerator is fixed and the denominator is getting very, very large, then the entire result will get very, very small. So the value of that limit is actually 0. And one final limit law that is specific to limits at infinity will be number 7. Again here, imagine that we have the limit as x approaches positive or negative infinity of f of x equals to infinity or minus infinity. In fact, I should say over here, if this limit is equal to positive or negative infinity, and let's say the limit as x approaches positive or negative infinity of g of x is equal to a fixed number m, then the following is true. Then it happens that the limit as x approaches positive or negative infinity of f of x plus g of x, that will be equal to the limit as x approaches positive or negative infinity of f of x plus the limit as x approaches positive or negative infinity of g of x. In other words, what this is saying is that even though this limit is infinite, we can still apply the limit law by applying the limit to each function separately. Again, something that we couldn't do with ordinary limits at a fixed number a. In that case, back in section 2.3, if one of these limits was infinite, we could not apply the limit laws. But here, with limits at infinity, even though we get one of the limits equal to positive or negative infinity, we can still apply the limit to every single function. And then if we do that, we end up getting positive or negative infinity, so plus or minus infinity plus m, and plus or minus infinity plus a fixed number m will equal positive or negative infinity. In other words, something like this is not an indeterminate form. With multiplication, we have that if we have the same conditions that I have here in black, the same conditions, then the limit as x approaches positive and negative infinity of f of x times g of x, that will be equal to the limit as x approaches positive or negative infinity of f of x times the limit as x approaches positive or negative infinity of g of x. And then in the first case, the limit is positive or negative infinity. And in the second case, the limit is finite, is m. Well, positive or negative infinity times something that is finite, we can conclude will be positive or negative infinity. So really telling us that this is not an indeterminate form. It is equal to positive or negative infinity.